Sir Harry Badeshia, I hope I pronounced it correctly, working out of Queen Mary University of London, an emeritus Tata Steel professor of metallurgy from the University of Cambridge. A passion, obviously, in all things steel, but an expertise that no doubt extends well beyond that. Can we please welcome you to the stage, Sir Harry? Thank you.
So, first of all, thank you all for surviving to the last lecture. And I have to say that I've really enjoyed the talks so far and learned a lot from the different talks. And there's a lot more I'd like to discuss during the dinner. So, I have a passion for steels, and I've been researching steels for 55 years now. Okay, so I'm much older than probably any one of you in this audience. And I was quite moved by the talk that Igor gave, where, you know, the motivation for his work was that there's roughly 700 million people who are malnourished. But because I'm very old, I remember the time when there were actually literally millions of people starving to death. Okay? And the thing that changed everything was steel. You know, the mechanization of agriculture completely changed the production of food. So we can now feed 8.1 billion people, I think that's the number that you mentioned, without any starvation ever being reported except in conflict zones. Okay? So the point that I'm making is that if you think carefully, you cannot survive without steel. Okay? And I'll give you several examples of this. Absolutely everything you do depends on steels. Your mobile phone, your manufacture of fertilizers, etc., etc. Having said that, I'm going to surprise you by saying that I would like a dramatic reduction in the amount of steel that we use, because we are using an indecent amount of steel every year, about 2.5 billion tons of steel. And I'm going to show you some magic. Okay? I want to show you a method of reducing steel consumption by 25%, okay, within the next 4 years, without causing pain to the quality of life that we have or to industry. Okay? And I'm not asking for a single pound of funding for this. Okay? This is completely does not require research or development. Okay, so we know, we can take it for granted that steel pollutes and that we cannot actually cope without steel. You know, the Paris Agreement, which actually is a very sound agreement, says that we need 50% reduction in emissions by 2030. That 2030 is not far away, okay? And if we don't do this, then the poorest people in the world will suffer the most, okay? Because, you know, you'll get flooding and all sorts of issues. Okay, so that's the case. And there is no time for research and development. We use 2.5 billion tons of steel every year. I'm not suggesting that all the ideas that have come out today and elsewhere are not worth investigating, but they simply will not manage to change anything within the timescales required. Okay? Okay, so I have a zero-cost solution to reduce steel consumption by 25% in 4 years without affecting the quality of life or without causing pain to industry. How can we do this? Okay, so I'm going to show you some real case studies, okay, involving all these things which take up steel in large quantities. And this is not just a hypothesis. These are real buildings which have been put up in a better way so that we save steel. And it's all written up in this book here on steels, which even the youngest in the world admire. Okay. Now, the first case study is actually from Brazil, okay, because I've worked with CBMM for a very long time. And back in the 1960s, there was an invention in Sheffield which should have won the Nobel Prize. If I was there at the time, I would have nominated 3 people for a Nobel Prize, because the addition of a very small quantity of niobium, and there was no niobium market before that, okay? Very small quantity, 0.03% or less of niobium into steel dramatically changes its properties. And we call that microalloyed steel. Microalloyed steel here. And what CBMM did was it did a beautiful study. This is the ordinary sort of I-beam that you would use in the vast majority of constructions even today in the world. But if you use microalloy steel, which is stronger, then you reduce the amount of steel that's needed by something like 22%. So what is the catch? Why don't we use microalloy steel all the time? This is the actual building that they put up, and I've seen this myself. Okay? And since this was put up, there have been several others, even taller buildings, because you require, originally when this was put up many years ago, you couldn't buy microalloy steel beams which are very tall, but now you can do that, okay? All due to CBMM in Brazil. And look, common sense, absolutely common sense. So microalloy steel is more expensive. You can see it's 6% more expensive, okay? But because you use less of it, the total cost is reduced to 83%. So you actually save money when you put up a building using the proper steel. Okay? This is just one example, okay? And I will go through several examples to show you that we don't need to do research and development. We already have materials which are far better than what we use. But of course, we are not using these better materials, and I have a solution right at the end to show you how to force that change. Okay, this is a bridge across the River Severn, the first bridge which was built. And, there is a cost in the construction of all these objects. And, a colleague of mine, David Collins, calculated the cost of putting up this bridge, which includes the cost of concrete and of the steel and so on. So this is a long span suspension bridge. And people like long span suspension bridges, even though there isn't sufficient traffic here to warrant such a wide span. So David Collins then looked at the second bridge, which was the Prince of Wales Bridge, which was built across the River Severn here. Much lower carbon dioxide cost, and the span underneath is wide enough for the sort of shipping traffic that you get. And by having all these pylons and the steel, you actually save a huge amount of carbon dioxide. So this is engineering, okay? So proper engineering, right from the beginning, you will save a lot of CO2 and reduce the amount of steel and concrete that is used. So the foundations here don't need to be as robust as the foundations for the suspension bridge that we had. And unfortunately, people want to get the longest single-span bridge. The longest single-span bridge is 2 kilometers unsupported, which is in between Kobe Island and Awase Island and Kobe in Japan. And the latest one is going to be across the Bosphorus Straits between Turkey and Turkey. But you do not need that sort of a span, okay? They just look nice. Now, here's a very topical story which I've analyzed in detail and paid a lot of money of my own to obtain the license for the images that I'm going to show you, okay? So this was a collision between 2 ships in the English Channel, and one of them was a tanker and the other was a cargo ship, a container cargo ship. The tanker was completely stationary. So I don't know how modern technology failed, but the moving cargo ship hit the tanker. And this is the damage caused on the tanker. And I want you to look at this very carefully, okay? It cost me about £200 to get the license for this image. there is massive damage, okay? But look at how the steel has deformed, right? And this is the reason why, you know, when you have a collision in a car, quite a severe collision in a car, you're able to walk out of the compartment, passenger compartment, with very little damage, okay? Because steel can deform and plastically absorb energy. And, you know, I enjoyed your talk on machine learning as well, because, you know, I myself use machine learning. But I have to say that, you know, carbon nanotubes and graphene, if you break them, they absorb zero energy. All the energy is recovered, all right? So you cannot ever make a safe engineering material just out of carbon nanotubes or graphene. I always have a go at graphene because they say it's 200 times stronger than steel, but actually it isn't. Okay, so look at this damage. One more thing you will notice is that the ship is still afloat, right? And I'm going to explain why. So it's a combination of steel, and here is a rough calculation that I did, which you could set for undergraduate examinations, right? To show you that, look, these are numbers that I've got from the interim report from the Maritime Investigation Agency in Britain. The Solong was moving at a speed of 16 knots, which I've converted to meters per second, and it weighs about 8.5 times 10 to the 6 kilograms. So you work out its kinetic energy, and it comes to 300 million joules. So just imagine how many chocolates that is, okay? 300 million joules. So the collision has to absorb that much energy, right? And the steel will be absorbing that energy. So if you do a rough calculation of the strength of that steel, it's about 400 megapascals, and the plastic strain it can tolerate is about 0.2. Then the steel absorbs 90 million joules per cubic meter, right? Per cubic meter. If I then convert it into area, and noting that the hull of the ship is 12 times 2 millimeters thick, I'll explain the two later, then about 9 meters of steel will be completely damaged, and that's roughly the right scale here, okay? There is no other material in the world that would have survived that sort of damage and kept the ship still afloat. And this is before the ship was damaged, and the reason why we had almost no pollution is because actually the tanker has 18 tanks. And according to reports, we're not clear whether one tank or two tanks were damaged, but very little fuel was spilled, and there are no reports of any animals suffering from that. Furthermore, it has a double hull, okay? So that's why I multiplied the thickness of the steel by 2, which means that, you know, there is quite a lot of safety built in, and that is a regulation required for tankers which are going to get anywhere near territorial waters. It does mean that you use twice the amount of steel, which is not a good thing. Now, one of my former PhD students, Kazutoshi Ichikawa at Cambridge, he's now at Nippon Steel. He and his team designed a new kind of ship steel which is much more ductile, so it can absorb a lot more energy. Now, this is a very easy test to show, but it's not at all good enough for anybody to accept your steel for a ship, because there are so many requirements, all right? You have to be able to weld it and lots of parameters. So it has to be strong, but not too strong, because then it won't be able to deform and absorb energy in a collision. This is really important. You've got to be able to join bits of steel together, and it has to be tough. That means when you give it a knock, it mustn't fail in a brittle manner. And you've got to be able to mass produce it in the right sort of shape. Furthermore, you have to go through all the specifications, agencies, government agencies, shipbuilding authorities, and so forth, to qualify a steel. So the team that developed the steel spent many, many years coming up with the solution. And I'm going to show you the large-scale tests that have to be done to prove. So first, this is the conventional steel that's used for the double-hulled ships. And this is a massive sort of indenter which goes into the material. You will see that it fractures at the top, okay? In which case you would either leak oil or water would get into the ship. So you have to do tests which are amazing in their scale, all right? So this has broken, and now I'll show you the newly developed material. The same sort of indentation, same sort of depth, and nothing will happen to that steel. Okay. Back in 2014, this was used to construct ships. At the moment, just bulk carriers, right? Because the regulations for tankers still are not adapted to the new steel. 2014, that's a long time ago, okay? And that means that you cut the use of that steel by a factor of 2, okay? Now, this is going to be more expensive, the steel, because it's very nice. And therefore, by using half the quantity, you pay actually less of a total content. So it's now in at least 20 or 30 ships. And hopefully it will expand further. There are also new technologies for making things, you know, and all of you will have played with Lego at some stage, where you make a layer and then you make another layer in a different shape and you build a nice object. That's exactly additive manufacturing, okay? Where you build up a component layer by layer into however complicated a shape that you want, including internal angles. This is a particular tool that's used in the automotive industry. And that is the new design by additive manufacturing. Uses 70% less steel, and it looks completely different because by additive manufacturing you can actually develop a configuration which is optimum for the application, whereas here you would have to machine, and machining has its limits. Okay? So 70% less steel used. Now, everybody thinks that electric vehicles are the savior of the world. If you look at, and let's just look at running costs at first. People say zero, but that's nonsense, okay? If you look at carbon dioxide in terms of per kilometer, in France, this Tesla only emits 26 because the French electricity comes from nuclear power, most of it. But the same car in the US uses 141 grams per kilometer. And this is my car, okay, which is less than the Tesla Roadster, because my car is 1,100 kilograms, whereas these cars are of the order of 3,000 kilograms. Now, if you include the CO2 cost of actually making the car, then I win by a factor of 3. Okay? And the amount of steel that goes into cars actually hasn't reduced, even though we have amazing developments in automotive steels. It's because of safety. All right? So the safety regulations have increased enormously, so even from side impact you have to protect the passenger compartment. So electric vehicles are not actually going to be the complete solution, because the cars that are being focused on are just too big, and that includes, for example, the Tata Motors Range Rovers, which are, you know, ridiculously heavy. It's about 3,000 kilograms in weight. And most people do not need a four-wheel drive and then so forth and so on to take their children to school, right? Okay, so we can save a lot of steel by using proper and careful choices in what we buy. So here is what I propose, all right? And I've said this on the BBC as well, that we need legislation, because without legislation nothing actually happens rapidly. And there is a really good example of this. The CAFE regulations, which were introduced in the USA to improve the efficiency of cars, have worked amazingly. So the amount of fuel that a car uses now is a lot a lot less than what we used to before the CAFE regulations. And the legislation should be as follows, that exactly what you had in one of your slides, and I wrote it down, it's the carbon border adjustment mechanism. Yeah. We need that for steel. So anything you import or make locally, you charge a tax according to the content of the steel content of the object that you buy and so on. And furthermore, that tax income doesn't go into Rachel Reeves' treasury, but it goes to industry to help them to get better technologies. There's another experiment in progress on a very large scale, which I have to thank Donald Trump for. Okay? We've had some things said about him, but this particular idea is very good. And that is that 25% tariffs on steel imports into the USA. Now, already the cost of steel in the US is rising because of this. Now, although the rise is still within fluctuations over seasons, but I'm monitoring this to see whether the increase in steel costs in the US leads to a decrease in consumption. And Donald Trump will be there for at least 4 years. So I hope that the 25% tariffs persist on steel imports so that I can have a real experiment to show you that this method actually works in reducing steel consumption rapidly. Okay? That's all I have to say. Thank you.